record. There it is. All right. Hello, everybody. Couple of people online, although I think maybe one or two more will pop in, and all of you in the classroom today. Thanks so much for coming to this talk, which is part of the 9th annual Women of Science event at Vanier College. Today, we are very lucky to have a distinguished speaker with us, Dr. Katanya Kuntz. She is a research associate at the Institute for Quantum Computing at University of Waterloo, and she is the KeySat Science Team Coordinator for Canada's first quantum satellite mission, which is the acronym KeySat stands for Quantum Encryption and Science Satellite. I have really no idea what that means, but I'm very, very excited to find out. Katanya received her PhD in electrical engineering in quantum optics from University of New South Wales in 2013, and a BSc in physics from the University of Calgary in 2008. She works in the field of experimental quantum optics, such as generating quantum states of light using lasers and nonlinear crystals to study quantum entanglement. She's active in promoting STEAM education, as she's doing today, via outreach in schools, the community, and volunteer work. So for this talk, I'm going to be monitoring the chat, and I'm also going to be monitoring the participants. You can feel free to put a question in the chat if you're online, or raise your hand if you'd like to speak. If you're in the classroom, just raise your hand. We can sort of see everybody, but it's hard to tell. So Nick is there, and if anybody has a question, just raise your hand, and Nick will pop in and interrupt so you can ask your question. And without further ado then, I will hand it over to Dr. Kuntz. Take it away.
Thank you very much, Carl. And thank you so much to the organizers and to all of you people out there right now listening. And I have this opportunity to bring some cool science to your classroom. So I'm going to share my screen. Okay. So as you just heard, my name is Katanya, and I work for the University of Waterloo at the Institute for Quantum Computing, and I am an experimental quantum physicist. So I'm going to talk a little bit about what that is and this mission called the KeySat mission. And often when I give these talks, I like to start with what my background is. So I graduated from Calgary, studying my Bachelor's of Science in Physics. And I actually did an undergrad project. If you want to do like grad studies and become a scientist, it's a good idea, especially if you want to be an experimentalist. It's a good idea to play around in the lab and get a feel for if you like it. So I got to actually make a lightsaber for my undergrad project. So that was a kind of a cool thing that the University of Calgary let me do. And then I flew to the other side of the world and I went to Australia. And if anybody ever gets a chance to study abroad, it's a fantastic opportunity. Not only do you get out of your comfort zone because you've left your little social bubble of your world where you are now, and you get to see how other people live in another country and in different culture perhaps, but you also grow your network. So in quantum physics, there's not that many people in this world that are doing this type of field, but it's a lot more than say 100 years ago. And in 100 years from now, I don't even want to guess, it's going to be massive, right? So the more people you learn from and that you interact with throughout your career, whatever you choose, is great. So I was very fortunate. I got to go to the University of New South Wales in Canberra, Australia. And I jumped from my Bachelor's of Science straight into my PhD, because in Australia, if you do an honors project, it's kind of like a mini master's like thesis. And so you don't have to go into a master's program. You can go straight into your PhD. And I love that because I felt like I was done with school and I just wanted to get in the lab and start doing cool experiments. So also in different countries, sometimes quantum physicists, laser physicists, sometimes we're in the physics and engineering, physics and astronomy department. So like in Canada, for example, it's usually that. But in other countries, you might get put in the electrical engineering department, which is really cool because yes, it's physics that we're dealing with, but then you actually have to measure the light. And that's detectors, that's electronics, that's analog digital filtering. So it's all electrical engineering. So I had this cool background where I started off in physics, and then I have a PhD in electrical engineering. So I can kind of talk with both groups of people, because sometimes physicists think a little differently from engineers, and engineers think a little differently from physicists, but we need everybody to think together. So then I flew right back to Canada, and I took up a postdoctoral fellowship at IQC at the University of Waterloo with Thomas Yennevan. He's my prof now, and I've stayed with him, and now I'm currently a research associate. So basically more like a glorified postdoc. And I'm going to talk today about this mission, but this is the part of my title is the KeySat Science Team Coordinator. So if you think about those big missions from NASA, for example, and you get those rooms full of like people behind all the computers, and it takes a lot of scientists, a lot of engineers, a lot of moving parts to make one of these space missions happen, or satellite missions happen. So I'm working with the Canadian Space Agency, and my boss, Thomas, he's the lead scientist on the science team. And so we're kind of like those people that are in the room with the big screens, and we're going to be launching a satellite in 2 years. And this is a little graphic of it. And so I've kind of fell into this role because I'm very good at science, but I'm also very strong communicator and organizational skills. So coordination comes very naturally to me. Some people might see trying to coordinate a huge science team like a whole bunch of noise and you don't know what to do. But I kind of just see like a whole bunch of people that are like, they're masters at their craft. It's like an orchestra. They all know how to play their instruments. And I'm like the conductor. And so I'm just helping them all bring this together, as well as add a couple science ideas myself. So I know that was a very long introduction of me and what I've done, but I think a lot of people might be interested in that. And so as I said at the beginning, my background, I'm an experimental quantum physicist. So what does that mean? So experimental, I like to push buttons and see a reaction in the lab. I play with lasers and I have mirrors and we send the light through nonlinear crystals, which is just a special type of material. And then it can generate these cool effects like quantum entanglement. And I could talk about entanglement later, but not right now. But what is quantum? Okay, quantum is just the study of the microscopic, the subatomic. So looking at the structures of molecules, looking at the structures of atoms. So if we want to understand the tiny of our universe, that's what quantum physics is. So you might have seen this picture before of our pictorial representation of what the atom looks like. And then this is a cool picture. This is actually a microscopic image of what chalk looks like. So like I have a whiteboard. I know everybody has whiteboards or like a digital thing, but in the olden days, we used to have a blackboard with chalk. Actually, in the Perimeter Institute in Waterloo, they still have chalkboards everywhere. It's beautiful. It's a little dusty though. So this is actually what chalk looks like on the microscopic side. So you can see the world that we see with our eyes can be very different from the world of quantum physics. And as we understand quantum, as we continue to do experiments, as we decided, as we came up with more theories that also coincide with the world around us. So like the experiments and the theory were one in one. We've developed our understanding of how the world works, like at this fundamental level. So these pictures here of the hydrogen wave function. So this is pictures of the different electron orbitals. So our understanding of how science works evolves, just like everything. So we started off thinking maybe it's like this with the nucleus in the middle and the electrons are orbiting around and stuff like this. But then we're like, oh no, if electrons are going around a nucleus, they're always going to be losing energy. Classical physics tells us they're going to spiral into the nucleus and atoms shouldn't exist. So that must be wrong. And that's when Niels Bohr came along and said, no, we got these stable orbitals. It's all good. The electrons can just hang out there. They can just chill there. And then if they want to move in between the levels, then they have to give off energy, then they have to absorb energy. And that's where we get photon. So what is light? Because I also said I'm an experimental quantum physicist, like optics, like quantum optics. So we play with light. So what is light? So light is just an electromagnetic wave. You might have seen this picture before. You got the electric field, you got the magnetic field. And light takes all different forms based on the frequency or the wavelength. So very, very long wavelengths, radio waves. And then you have microwaves. This is all light. This is all electromagnetic radiation. And the stuff that we see with our eyes is just this little tiny portion, which is not really to scale on this diagram. It should be much smaller. But it's a tiny portion of the visible range that we can actually detect. And it goes all the way up into very, very, very high frequencies, as you know. So one thing I want you to keep in mind is polarization. So when we're talking about light, we can talk about its different labels. So it has a wavelength, right? It's red light, blue light. It can also have polarization. That's a label. And we just had to choose direction. It's just a way to organize our coordinate system, basically. So along the electric field, that's our polarization axis. Now, remember I said a photon. Now, what is a photon? A photon is a particle of light. And it's a unit of energy, okay? And the cool thing that quantum physics revealed is that light acts like both a wave, like a water wave when you get interference, like you can see in this picture. But light can also act like a particle, just like marbles. And so the flip side of that is that matter can also act like waves or particles. So my naive brain always thought of atoms as particles and energy, light, as a wave, because I could easily see interference patterns on the walls, or when you're outside, you can see light interfering with itself, right? You wouldn't think of that as particles, but if you actually change the way you're looking at the light, if you change the way you're looking at reality, it can flip. It can flip between this wave-particle duality. And sometimes it's more convenient to talk about light in terms of particles. So when I'm talking about how we use light to transmit a code, which is what I'm going to talk about in a bit, it's easier to think about that code in terms of bits, in terms of zeros and ones, in terms of discrete little chunks. And so it's easier to think about photons in that way. So you're thinking about light, think about these little discrete individual chunks. And each chunk is going to be this 0-1 bit thing. And the 0-1 bit thing is going to be dependent on this polarization state. So that's just an overview. Don't worry, there was just a little bit. So I want to pause now, make sure everybody's okay. Are there any questions yet? I haven't really said anything big yet. Just interrupt me if there are any. Okay. So I'm going to talk to you today about this quantum key distribution. What is quantum key distribution? Why do we need it? Why should you care, right? So when you're dealing with security, information security, any type of communication where you need to be sure that your message is secure. Currently, we have these public key encryption, okay? And a public key encryption is based on a type of algorithm, a type of mathematical equation, and it's factorizing large numbers. It's really hard for computers, normal computers, like the computer I'm talking to now, a classical computer, a computer that's using electrical circuits to do the computing, right? And we just save the information as 0 or 1. I mean, that's it. So this public key encryption, it's based on factorizing large numbers, and that's secure because our current computers cannot hack that. It takes the age of the universe to factorize really, really, really large numbers using our normal classical algorithms. But then with quantum computing is basically using a different type of platform to do computing. So some people have made this comparison where a classical computer is like a candle, and then a quantum computer is like a light bulb. They both produce light, but they're very different things. The physical mechanisms to produce light using a candle, that's burning a flame, right? Electricity is a very different thing. So in a quantum computer, you're using quantum bits. You're using atoms, electrons, you can use photons, basically something that's a quantum bit to do the computing. And in classical computing, it's an electrical signal. It's an on-off. It's a 0 or a 1. It's never both. If your computer gets stuck halfway, it breaks. There's always a threshold. So that's why with classical computing, these problems take forever. In quantum computing, you now have this quantum bit. So you can have this 0 or 1, 0 and 1, like at the same time. It's in a superposition state. So when you're doing certain algorithms, certain mathematical codes, they can go faster because it's like every little bit in your quantum computer is doing its own version of your calculation. So say you had to do a repeated calculation, the same thing, exact same thing, 10 times, but you had to change the number every time. But you have to do it one at a time. Okay, so if you have a quantum computer, you could do all 10 of those versions of the calculation at once. So the security, so this is telling us that public security, public key encryption will be vulnerable to the abilities of quantum computers. But this is why quantum key distribution has been developed and has been developing ahead of the quantum computer. We don't have a quantum computer right now. There's companies that make things that are like quantum computers, act like quantum computers, but they're not fully quantum. There's lots of arguments about that. But QPD,
I've got a question, sorry.
Yeah, go on.
So the question is, how much does a quantum computer cost?
Right. It would cost, you can't just buy one right now. There's governments who are leasing time on these adiabatic quantum computers, and I think it's millions of dollars, but I'm not sure.
I've got a question. How do you make a quantum bit? What exactly does that look like? I can picture a switch being on and off, but I can't picture a quantum bit.
Definitely. So a quantum bit is going to be, if you imagine an electron, okay, an electron has this quantum quality called spin. And so the electron, it can be a spin up or it can be a spin down. And unless you actually measure that spin, it's flipping back and forth. So you can't really visualize it because quantum spin, it's not actually an electron spinning on itself, right? But that's the way you can kind of visualize it in this way. So until you actually collapse that state, it's both up and down. It's in this like fuzzy superposition. Whereas with a light switch, it's on, it's off. If you put it halfway, you start to like cause like sparks to fly out your wall. Does that answer?
I've got another question.
Using the switch analogy, so would it be kind of like I don't get it. I don't understand.
We don't quite understand the switch analogy. So how do we measure if it's both on and off? What is the measurement there?
Oh, I see. Okay, so in the classical computer, there's only one option. It's either on or it's off. That's it. In the quantum computer, you have both on and off simultaneously. And until you look at it, until you take a measurement, taking a measurement in this case, literally taking a picture. So we can photograph individual atoms. We can take images of atoms because there's people that have actually lined up individual atoms to spell like IBM and stuff like this. And so if you take a picture of those atoms, you're freezing them in that moment of whatever they're doing, right? And that's a measurement. So the electron, the quantum bit, it's going to be like hovering between the 0 and the 1 until you take a measurement, which can literally just be like a photograph.
Good with that? Thank you.
Cool. Yeah, this was kind of just like I kind of diverted into a little the recording.
Sorry, that was me. I accidentally hit my keyboard. My apologies.
That's okay.
Back on again. Keep going. Sorry. I'll fix that in post.
Oh my goodness. I'm glad that we're doing this talk this week and not last week, because I got sick over Thanksgiving long weekend. And if I was delivering this talk last week, it would not have happened. So this is good. If I start coughing, that's why. And no, it's not COVID. It's all good. Okay. So I'm going to go back. So now we have this quantum computer. And the whole point is that these quantum computers make our current encryption methods vulnerable. So we need a replacement method. And we've known about this for a while. And so we have tons of people around the world working on this. They've been working on it for decades. There's companies that sell devices. It's being handled, okay? Don't everyone freak out that your banking is now insecure. No, it's okay right now. The point is that the security of this new technique, the quantum key distribution, it's not based on computational hardness of solving these mathematical problems, but it's actually based on a physical process. And so it's not vulnerable to these attacks. So if an encryption key is generated by a QKD protocol, if it's considered secure today, then that means it will remain secure in the future. And that's actually something called forward security, which is a very good thing. So you want that, you want this, right? If you have information today, you want it to be secure always. And so as I said before, a photon is this particle of light and it can carry a unit of information. And so we call it a quantum bit, short form qubit. And quantum information, it can be transferred, okay, from A to B, but it can never be copied. And the measurement disturbs the system or the state. So never being copied, that's called the no cloning theorem. And it literally just falls out from the math. I can show you if you want, but it does. Because basically if you try to copy a quantum state, you're not allowed. It's physically the mathematical equations prevent you from being able to copy a state. So when you do teleportation, so like I'm a huge Star Wars, Star Trek fan, awesome. And in Star Trek, in Star Trek, teleportation, right? We want to teleport from one place to another. Well, you're not copying Spock and making multiple Spocks, right? In quantum teleportation, same thing. You actually have like two entities, okay, I don't want to talk about this. The point is that you don't actually copy, you transfer the information. And then the measurement disturbs the system. We just talked about that, right? So if you have a particle and then you take a measurement, you take a picture of it, it hits a detector and it goes in from being a light state into electrical signal, right? Because it's gone from light to a detector to electronics. That's a measurement. Measurements disturb the state. They destroyed the photon, right? To measure the light, you're destroying the light because it's interacting with your detector. And then that detector is transforming those photons into electrons that then become an electrical signal, which then you can read on your monitor, right? So because of those two principles, this is safe. And I will explain this. I'm going to go through actually a basic QKD protocol. So
okay, can you actually hear me?
Yes, I can hear you. And I also sense that somebody wanted to say something.
Question. It might be a minute or two back.
I was asking for an example of quantum information.
Could you give us an example of quantum information?
Yes. All quantum information is, so information is, so when I speak in words, right, that's information. So I'm speaking in a language, English. we can then transport that into just these zeros and ones, right? So that's also a language. So the zeros and ones of binary code, that's a language, that's information. So when I say quantum information, I mean storing, transmitting zeros and ones in a quantum system. So I'm going to show you what I mean by how you do that with light. So we're going to use, we're going to go through it, but that's what I mean. And then you can also use electrons to store information. And
Good.
yeah, quantum information just means it's information that's, and we're using a quantum store, like a car. The little car is going to drive a book. Okay, the book is the information, the car is the mode of transport. And instead of using radio waves, because we could call, or microwaves, right? We could use a phone and we could call each other. That's not quantum, that's classical. And why? Because you're not just using one photon per information bundle, you're using a bazillion photons. Like there's a whole bunch of photons in one of those electrical signals, radio wave signal. So it's not quantum. Once you get a whole bunch of photons, once the light state becomes big, macro means big, right? Micro means small. So for it to be quantum, it has to be in the micro scale. As soon as you cross into the macro scale, then it's classical. And then classical information can be copied. We do it all the time. Control C, Command C. Yeah.
Thank you.
And there's one more question in the chat, perhaps. I'm not sure.
That was me.
No, I think that was Nick.
Okay, cool. All right, cool. Okay, so that was very big. So I want to just kind of pull it back. Why again do we care, right? So big picture, real life problems. Say you are in the Navy and you have these two ships and they're on the ocean. And the two ships, they need to communicate with each other. But satellite communication has gone down. And this is actually a serious problem that we are working on. So satellite communication has gone down. Their normal ways to communicate is not possible, or it's been corrupted. So these people, they need to establish some kind of a free space through the air, a link that can transmit information. So you can have USS Alice, right, and USS Bob. And the way that in quantum key distribution and all this kind of stuff, it's always Alice to Bob. The easiest way to remember that, A to B, Alice to Bob. So Alice is transmitting, and she's going to have a telescope, and that telescope has like a laser system also part of it. And then it's going to she's transmitting the light to Bob. And now Bob has the receiver, also a telescope to collect the light. And then Bob will have some detectors and some electronics and stuff like that. Okay, so say Alice and Bob want to communicate securely using photons. So if one thing that you want to also, I'm trying to figure out how to, okay. So the part of this real life scenario that I was helped investigate was if you're using a laser and this is on the ocean, okay, so you're just above the ocean, atmospheric turbulence is going to mess up your light. So atmospheric turbulence, what the heck is that? If you're looking at the stars and you see them twinkling, that's because the air between your eyes and the starlight is moving. And so the light that's traveling through the air, it's breaking up, and then it's darting around and moving in place. It's called scintillation. And there's also patches of hot air and cold air. And so the different changes of indexes of refraction, because of the heat changes in the air, that moves the light, because light will shift with different indexes of refraction, that the path will change. So above the ocean, you definitely have the worst turbulence, because you have this giant heat mass, right? And there's always like clouds, weather, air rising, stuff like this. So what we wanted to investigate is how would that affect Alice and Bob's ability to communicate, and also how would it affect someone who's like in a little tugboat or something, right, out in the ocean, and they want to hack, they want to attack Bob, they want to hack and try to learn the secret key, because they can try, right? No one's preventing you from trying. We just said you can't clone it. So if you tried to steal one of those photons, copy it, and then give it back, you can't. So there's some methods of hacking and attacking that doesn't work, but there's this gray area where maybe you could like mess around if you send in your own laser to this receiver. So we needed to study what happens to a laser through the atmospheric turbulence. And so in the lab, we don't want to do this out in the ocean, right? Like it's a lot easier to do controlled settings in a lab, to do the experiments, and then go outside for the real world test when you've already learned a lot, right? Get your feet wet before you jump in the pool. So we wanted to study what happens to the laser before and after turbulence and how it affects the system. And so this picture here, it's a false color image of what the laser beam looks like when it's being transmitted from Alice. And so dark red is really, really bright. And then the blue is very, very dark. And so you can see it has a bright center and then it fades out. It's Gaussian beam. That's the Gaussian shape that you're looking flat on. So it's as if I took a camera and I put it straight into the beam. The light hits the camera. I take a picture. That's what it looks like in the false image. Okay. Now in the lab, I had this special device called a spatial light modulator. And remember when I mentioned how turbulence, it's that changing of indexes of refraction that cause the light to like move around and chop up and get all messy. So you can create that kind of stuff in the lab using a hologram, which is this black and white image here. Okay. And so black is one phase, white is pi phase away. So 0 to pi. And the more dark lines closer together, the more turbulent the light would be. And so choppier the air. And so if you take a beam after turbulence, it's all broken up like this. You can see like there's a couple bright spots in the middle, but it's all kind of scattered and it's big and it's messy. So we know that's going to happen. But then this telescope just has to be big enough to collect enough of those photons to have a big enough signal, and then Alice and Bob can communicate. So it's not too bad. But now, what if Eve, the eavesdropper, now what if she was in that little tugboat, right? She's hiding out in the ocean. She has her own laser, and she can shine the laser into the receiver. And then if she gets that angle just right, maybe she could make Bob's detector act in a funny way that only she knows she's causing. And so she can like couple herself into his system. So she can learn about what's going on between Alice and Bob because she's manipulating what Bob is receiving at some level. If the manipulation gets too high, we detect it. We detect it because, as I said, measurement disturbs the system. So if she starts trying to mess with Bob too much, there'll be all these errors that didn't make any sense. The error rate will be too high, and there'll be like a, an artificial like alarm that will go off, being like, no, your channel's been corrupted. You need to check something. Okay, so if you want to learn more about this, I'm happy to talk about it. You can also find our paper online. It's also on archive, so you don't have to have like a subscription to a journal to read it. And so this is like a big picture of like, why would you want to use QKD and how could it be useful in the real world? Now, I mentioned that we're going to be talking about space, obviously, and satellites. So there's a quantum space race that's currently going on. And there's countries all around the world that have already launched satellites or are in the process of launching satellites that demonstrate quantum communication. So for example, in China, the Meteor satellite was launched in 2016 and has already demonstrated several big quantum experiments. So there was a link between China and Austria and they had a video link that was quantum encrypted. So a proper like, you know, Skype call that had QKD as the encryption. So that was a real world demonstration, first of its kind. They also demonstrated the longest entanglement links. So entanglement is this like funny correlation thing, right? Really, really briefly, just hand wavy. Remember I said I work with lasers, and lasers go through nonlinear crystals, which is just a type of glass that has a nonlinear properties to it. And so one of the properties is you could send green light into the crystal, and red light will come out. Like some of the green light will still come out, but there'll also be red light that's produced. And so what's happening is that one green photon is actually converting, it's called parametric down conversion, into two red photons, particles of light. So the two red photons, because of energy conservation laws, right, they sum up together to be the same as a green. But because the two red photons originated from that same green photon, they have this like magical correlation property called entanglement. And so if you take those two red photons and you send one up to one of your satellites and you keep one down at the Earth, you can actually do entanglement experiments and tests over these like distances of like 500 kilometers. If you do it between satellites or different ground stations, you could do it over like 1,500 kilometers. And so we're testing, does this funny correlation stuff that holds in our labs, right? When we do these experiments in our labs, the light is being transmitted over a few meters, like 5 meters maybe. If we had fiber spoiled up, like optical fiber, then maybe we could do a couple 100 kilometers. But in free space, no. You'd have to have a bazillion meters to do that. So it's usually the path lengths of where we're testing these quantum properties. It's over a few meters. And the really cool thing, and this is part of the fundamental science part of the mission, is we have like the quantum physics that's describing the tiny, and then we have like general relativity, right, describing the macro, describing how you know, planets work, how the big universe works at that scale. But if you start to do these quantum entanglement experiments on a length scale of macro, right, 500 kilometers, that's definitely not micro scale. Do the principles still hold? And so far, the data is showing yes. And we're even going to be doing experiments like involving the moon. So like NASA has a project called the Lunar Gateway coming up. So they want to have like satellites that are like orbiting the moon, and we're doing like quantum experiments between the Earth and the moon.
I've got a quick question.
Yes.
Word entangled. What exactly about these two red photons is entangled? So, are we looking related?
Very good question. So the easiest way for me to explain that would to take the polarization version. Because like I said, light has lots of different labels. So it could be entangled in energy and time, but it could also be entangled in polarization state. So you can have like, but that's the easiest way to think about it right now is polarization state. So if you had a horizontal polarization and a vertical polarization, right, they're orthogonal to each other. So if one photon, you measure it and ends up being a horizontal, then depending on how your experiment has been set up, right, that could automatically mean that the other photon is vertical. And so if you had a horizontal photon up, you know, sent over to the moon, and you kept your vertical photon on Earth, and then you did the measurement either on the moon or on Earth, the cool thing is that so far it seems like there's like an instantaneous, it's not information transfer because you're not transferring information, but the state collapses instantaneously. So if red photon 1 is H, red photon 2 is V, and there's no time delay. They don't have to talk to each other. It's just instant. So like an analogy is when you have two twins and you tickle one and the other one starts laughing instantaneously, right? Yeah.
I paraphrase that just to make sure I'm understanding.
Mm-hmm.
So we know that between the two photons, exactly one is horizontally polarized and exactly one is vertically polarized. We just don't know which one is which. But when one person makes a measurement, it forces the other choice on the other observer. Am I saying that correctly?
Almost, yes. The two photons, they're like spinning, they're like hovering between horizontal or vertical. So they're in this fuzzy, they're both in this fuzzy superposition state of being either horizontal or vertically polarized. And until you make a measurement, they're in that state. And then when you make the measurement and you discover, okay, this one is horizontally polarized, then the other photon has to be vertical. And that's when they become a defined state.
Thank you.
Awesome questions. Okay, and so you can see here, there's one of the ground stations that they decided to show in this article is IQC, and our airplane demonstration, which I'll show some pictures of in a little bit, that was done in 2017 and 2016, 2017. And then our KeySat mission, the satellite mission, is coming up, and we're going to be launching it soon. Okay, so I thought it would be good to just kind of step through at a high level. How does quantum key distribution work? And so I want to start with this like BB84 protocol, named after Charles Bennett and Gilles Broussard. They were the founding fathers of QKD, and so it's named after them. And it was actually designed in 1984, so that's why the 84 is there. So it's been around for a while. So remember, we're going Alice to Bob, A to B. So Alice is the sender, Bob is the receiver, and in the gap between them, that's the quantum channel. That's where we're sending our photons. And each little arrow in this picture is representing a different photon traveling from Alice to Bob. And the idea is that we want to make up a code. We want to make up some kind of encryption code or an alphabet using the light. So we want to make up a whole bunch of zeros and ones that can be used to encrypt a message. So we're not sending the message right now. We're just trying to create this code. So when I was in school, we didn't have cell phones in our classes at all. And so if you wanted to send a message to like a friend in the class and you didn't want your teacher to be able to read it and stuff, right? You would come up with some kind of a scheme. You would say map A to H and B to G, and you make up some kind of an alphabet scheme, right? So that it would be all gibberish if someone was to read your note. But then if you had the encryption code and the decryption, then you could make it English again. Okay, so what we're trying to do is essentially kind of like this map where we're making one letter into something else so that it's gibberish to anyone else. But instead of using an actual alphabet, we're just going to use like zeros and ones. So all quantum key distribution is this real-time generation of an encryption key between Alice and Bob, where each photon is just carrying one qubit of information. So the picture that I showed before, where we have the electromagnetic field of light, and we're talking about, in this case, the polarization state, which is just how is the electric field aligned. And so for the polarization state, we're going to assign some zeros and ones. We have to make this map. And so we decide, okay, a vertical polarization is going to be a 1, and horizontal is going to be a 0. Okay. And then because of the way the protocol works, you also need a second set of photons, basis. So we have the linear basis, and then we have diagonal basis. And so diagonal basis is just that mixture. It's that 45-degree offset between horizontal and vertical. So you have diagonal and anti-diagonal. And so now this is our map. So each photon is going to... Yeah.
Does it only have to be 45 degrees, or can you choose the angle?
For the polarization, does it have to be 45 degrees, or could we change the angle?
Yes, it has to be 45 degrees because you'll understand why in just a second, but that's part of the algorithm. It has to be 45 degrees because then when someone tries to take a measurement, they don't know what to do. Was it an H or a V? If there was a skew, if it wasn't diagonal, if it wasn't 45 degrees, if it was like 22.5 or something, then they would have a higher chance of guessing it correctly. I don't know. It's part of the like 50-50 guess part in a minute. Any other questions?
Well, a question to that: is it a matter of resolution, or just?
No, it's the matter of if you send diagonal light to a what's called a polarizing beam splitter, which basically it's a partially reflecting mirror that separates light based on its polarization. So it transmits horizontal and it reflects vertical, or vice versa. And so if you have a diagonal photon coming up to that beam splitter, it has to make a choice because it's one. I'm getting ahead of myself, but that's why. You'll see in a second. Yeah. Okay, good. Okay, so we have this map. So 1 is for V, 0 is for H, 1 is for D, 0 is for A. Okay, zeros and ones. So step 1. Alice has to choose a state to send. So Alice has preferably a quantum random number generator to make a random choice, because you don't want any patterns in your key. You want everything to be completely 100% random. Any correlations in your zeros and ones, that's like gonna tell an eavesdropper a pattern. So you want, if an eavesdropper is trying to listen in to any of these photons, she just hears noise. That's what you want, randomness. So Alice chooses HVDA, one of those to send. Now, this is where Bob makes the measurement. So Bob has to choose, am I gonna make a measurement in the linear basis, so HV, or the diagonal basis, DA? And so again, this should be like preferably a quantum random number generator. And this is the cool thing about quantum information, single photons. If you send a single photon to this partially reflecting beam splitter, say this here was just a 50-50 beam splitter, not polarization based. So you can see there's polarization beam splitters here in these green blocks. You can also have a partially reflecting mirror that's non-polarization based. And so the light will hit that. And if it's a photon, if it's an individual particle of light, it can't split. It can't separate. It can't be an egg and just all of a sudden like go in two. Imagine an egg, it's uncooked, right? A raw egg. And okay, well, if it hits the mirror, it's gonna splat, but let's pretend it doesn't do that. It has to choose. It has to choose one path or choose the other path. It can't just break apart and go both ways. That's not how quantum physics works. This is one of the fundamental key components of why this works. If it's if you save your information as individual photons, when it comes up to a beam splitter, it has to make a choice. So it makes a choice. It goes to either HV or DA, okay? And then there's some detectors here that take a measurement of the light. And this polarization beam splitter, it's just separating the polarization state. So now you're gonna have these 4 detectors, and they're all gonna click one at a time, hopefully, if you worked everything out right, because there should just be one single photon coming in, and then it has a choice, and then it gets measured, and that's it. Okay, I haven't explained yet why we needed AD, diagonal anti-diagonal yet. Now we will.
All right. I was going to ask a question, but I'm going to let you go, and maybe I'll ask my question.
You ask questions, please, go on.
Well, no, but I think you might answer it, so go ahead.
Okay. Okay, so why do we care about this? You know, why do we need this 45-degree offset, right? Now, let's see what happens. Let's step through a protocol and see what happens. Say Alice is sending a photon and she sends one of the diagonal photons, right? Bob has no idea what Alice is doing, okay? So Bob is making a random choice and he's choosing to measure in either the HV or the DA basis. If he was to choose the wrong basis, right, because if Alice is sending it in the diagonal basis, for Bob to get a perfect answer, okay, a perfect, now there's no such thing as perfection in experimental, right? But you get close. So if there was this perfect detector and you have this photon coming along, let's pretend for now that Bob didn't measure in the HV basis, okay? Bob is going to measure in the diagonal basis. Let's follow that along. Okay. So if Alice sends a diagonal photon, take this little green one here. It's right there. And then Bob chooses to measure in the diagonal basis. Okay. What's going to happen is that this photon, right? It has like the diagonal polarization. It's going to hit this beam splitter. And it's going to go to this detector, this one detector here. It's not going to go to 0 because the beam splitter, the polarization beam splitter, it's going to separate the D from the A's, the diagonal from the antidiagonals. And one of those detectors is going to click because you only sent one photon. So if everything goes well, right, Alice sends a photon, say it's this D one, and then Bob measures it, say he chooses correctly, measures in the D, gets a photon, great. We got a photon, we got a detector, everybody matches. So we save that one as a good photon. Why do we save it as a good photon? Well, let's see what happens if Bob does the wrong way. Now, wrong just because it's random. So this might happen once in a while. So we need to be able to identify these things. This is why. So a diagonal one is going to come in. Now, say Bob chooses to measure in the linear basis. Okay. And so it has this beam splitter that it's going to measure in H or V. So a diagonal photon, it's half H and it's half V. It's diagonal. So if you break up the energy, half of the light is going to go to, well, if it was a classical signal and you had tons of light, right? Half would go to one detector, half will go to the other. But this is a single photon. It has to choose. So which one does it go to? It's 50% H, it's 50% V. Which one would you go to? You don't have a choice. It's random. It's all random. So if Bob makes the wrong measurement, wrong is in the wrong basis, it's a random answer. Is it 0 or is it 1? It's random. So that randomness would add noise, right? Because Alice, in this case, was trying to send a 1, right? Well, what if Bob's 0 detector goes off? Well, now that's wrong, right? Alice was trying to send a 1, Bob accidentally measured a 0. So anytime that Bob makes a measurement that's in the wrong basis, you have to sift that bit and throw it out. How's that?
Well, so you did answer my question, but now I don't know how you determine whether it was wrong or not.
Aha, that's because after they do this, right? So you build up all these like zeros and ones. There's a public discussion and it's called sifting. So in this chart, we got like the quantum transmission part. So the quantum transmission part is the Alice sending the light and Bob taking a measurement. And they do all that, and that's great. And then once it's all done, they talk to each other classically. So like over the internet, over the normal telephone, something like that, right? And all that Bob does is tell Alice the basis choices that he made, okay? Which is also just randomness because he's not announcing the answers. He's just announcing what choices he made for every time that Alice was sending a photon. So the two of them, Bob announces that to Alice. Now Alice knows when they were when they agreed and when they didn't agree. And so then they throw out the ones where they didn't agree and they keep the bits that did agree. And then this string at the bottom, this 1, 1, 1, 0, keeps going. And that's your secret key that is secure.
I imagine you'd have to do this repeatedly, many, many times to get the secret key, because you're throwing out stuff that you needed to keep if you only did it once, right?
Yes. Yes, but that's also part of, like, you need to, right? You need that randomness. You need that if Bob chooses wrong, then he gets a random choice. Because what about Eve? Eve will make those measurement mistakes too. So if Eve was to try to, and this is one of the attacks, it's called, I'm blanking on the name now, but it's an attack. And so Eve can try to take a photon, right? Make a measurement, make like a weak measurement, so it doesn't disturb the system too much, but it's enough that she learns something, and then like sends the rest of it off to Bob. If she has to make a choice, she has to make a random choice too to make the basis choice. So if she is wrong, then she gets randomness too. So that you have to have that part.
And I think, you know what, instead of me trying to explain it and doing a terrible job, I'm going to ask you to go back and just, there was a question a little bit earlier about why it needed to be 45 degrees in the diagonal. Could you just go back and bring that in now again? Because I think I understand, but I prefer to have you explain it than me butcher it.
No, it's all good. It's all good. Yeah, the 45 degrees is just because that's that, 50% horizontal, 50% vertical light. So to get diagonal light, it's, I wish I could see my screen. Can you see my whiteboard?
Yeah, sort of.
Any better?
Yeah, there it is. Okay.
Okay, so if this is horizontal and that's vertical, this is your light vector for diagonal, and it's made up of 50% H and 50% V. So when a photon that has this diagonal polarization hits this beam splitter, it has to make a choice, and it has to choose either detector 1 or detector 0, and it's random. So if you had light that was like more horizontal, less vertical, then it would have a higher probability of that light going to the horizontal detector than the vertical detector, and then that would be like a bias. And then an eavesdropper would be able to hear that. An eavesdropper would be able to be like, oh, Bob's 0 detector keeps going off way more because my 0 detector keeps going off way more because I'm tapping into the signal a little bit, not enough that it's disturbing the system too much. Like there's a certain level of noise that we can correct for. So yeah. Does that help?
Yes, absolutely. That makes perfect sense.
Okay, good. Any other questions from the room?
What happens if Eve, in this case, takes the photon and then just like substitutes their own, and Eve drops on the conversation, at like the public conversation?
What happens if Eve takes the photon and then puts her own one in?
Yes, that's exactly the attack that I'm trying to remember the name of. Man in the middle. It's called the man in the middle attack. And that's exactly one of the ways. So if Eve could, theoretically, because when we're doing the security for these types of protocols, we give Eve like superpowers, okay? We don't have quantum memories. Currently we do not have like a hard drive for quantum bits. We're making that, right? But we pretend like Eve has a quantum memory. So Eve could perfectly store a photon, right? Make a measurement and then send on another photon because she destroyed that photon. So she can't send it on again. She has to send on a new photon to Bob. So in this man in the middle attack, Eve has to still make a measurement choice. And so if she chooses wrong, the photon that she sends on to Bob will also be wrong, right? So say Alice was sending a 1, like a diagonal, Eve measures in the linear basis, gets a 0, gets a V, and then sends on a V photon to Bob. Well, Bob was expecting, and Alice was expecting Bob to get a D photon, not a V photon. It's the wrong photon. So that's going to be an error. And then every time, because maybe Bob does measure, this is how you detect the errors. Maybe Bob does measure in the correct basis, so they all line up. Say this one here. Say Alice sends a vertical, Bob measures in the vertical, gets vertical, everybody's good. But what if Eve actually intercepted it? So Bob measures in the correct basis, but she sent the wrong photon. And so Bob ends up getting a 0 when they were expecting to get a 1. And so that's an error. So you're always checking the error rate in the system. So if the error rate gets too high, then that can indicate someone is trying to hack your quantum channel.
Does that answer it?
Didn't you just indefinitely waste the people's time if you get them just sending the wrong one?
Could Eve indefinitely waste Alice and Bob's time?
Yeah, that's another attack. You can also blind the system. So you could just like I think it's called denial of service attack, and where you just like saturate your Bob. Like Eve can just saturate Bob with a laser so that Bob can't see anything. You just gets this like noise all the time. So yeah, these are the types of attacks, and I'm not sure how to mitigate that. I'm pretty sure you have to like reset your system and yeah, because if someone has sabotaged your quantum channel and is manipulating it to that level that you can't even establish a link, you got to stop. Yeah. Any other?
I think we're good.
Okay. So that was the BB84 protocol. And like I said, big picture, if you wanted to transmit information using a laser through free space, through the air, that's the way you would do it. And then you also need to consider in real life other stuff that's going to mess up your beam. And so to go back to space, when we're taking these experiments, these QKD experiments, and we're taking it out into satellites and stuff like this, there's a whole new range of interesting issues we have to come up with, solve. So I'm going to talk about that now. So what is satellite QKD? So I think we've got a good grasp now. If you have Alice and you got Bob. Now, what if you had a satellite that's in the middle, and why would you need that? So say you have two cities that are very, 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 very separate. And as I said before, quantum information, the quantum state, it's fragile. It's sensitive. It doesn't like it if there's too much noise, okay? So our normal internet right now, it's based off of fiber optic cables, and it is using light, it's using lasers, but it's using classical light. It's using tons and tons and tons and tons and tons of photons. It's not the quantum level at all, okay? So if you need to send the signal further, you can just boost it. So we just have all these like amplifiers, classical amplifiers, to boost the signal so that it gets around the world, okay? What is an amplifier? It's basically a cloning machine. It's taking a signal and it's making it bigger by amplifying it and cloning it and copying it, and right? You can't do that with quantum information. You cannot clone quantum information. You cannot amplify quantum information. So you have a problem. If you lose too much of your signal, at some level, you can't make it come back. So, and you can't just boost it up. So if we had these two cities and they're separated by more than 300, 400 kilometers, we can't use fiber optic cable to send the signal between them with the quantum information. We can't just use our normal fiber cables. It's too lossy. Every kilometer of cable has a certain amount of loss, light that just leaks away into the environment as heat. And so that's information that you're losing, and you can't reproduce, you can't replace it. So if it's lost, it's lost. So what do you do if you have two cities that are separated apart more than 300-400 kilometers and they want to have this secure quantum communication? Well, we can use a satellite. In this case, I'm going to talk about a satellite in a trusted node. So you trust the satellite. So you have a satellite and you have a ground station and you have your city A. And in this configuration, right, the satellite is going to be receiving, because in our scenario with our KeySat, it's the receiver is on the satellite and the transmitter is on the ground. So it's an uplink. You can also have downlink, where you have the lasers and stuff on the satellite and you have the receivers on the ground. There's advantages and disadvantages to both schemes. Ours is up. So you have Alice basically as the transmitter on the ground and Bob is on the receiver, okay? And so you do your QKD, like we were just discussing, using photons with satellite A, or with city A and the satellite. Then the satellite will move in its orbit until it's over the second location, ground station, in city B. And now the satellite and the transmitter in the city B, they do QKD, they generate a key, okay? And now the satellite knows both keys. So there's key A and there's key B. And those are the zeros and ones that we just built up, right? And because the satellite is trusted, in this configuration, it knows everything. It's like all knowing right now. So then the satellite, because it knows both, it can do an XOR operation, and an XOR is just that bitwise operation. If you have 0 plus 0, it's 0, 0 plus 1 is 1, right? So the satellite knows both keys, but ground stations A and B, right, they only know their key. So for A and B to talk to each other, they need to have a shared key. So what the satellite does is it takes an XOR of the two keys, announces it, because a public announcement of two random an XOR of two random bits, bit streams, is another random bit stream. It's useless information to anyone listening. So they announce, and then there's like an agreed upon key. Say everybody's going to use city B's key. So city A just has to do an XOR operation with that announcement key from the satellite, and it gets back key B. And because city A knows the key, right, they are the ones that are able to back engineer and get the shared key of city B. So that's how satellite QKD works with a satellite that's trusted, and why you need it. So to build up to doing an actual satellite mission, there's a lot of groundwork that goes into play. Thomas, my boss, and his team, they've been working on this for over 10 years. One of our first demonstrations was to put the QKD receiver, because remember, this is the receiver that's going on the satellite. So it's moving, right? It's going to be tracking across the sky. So they mounted it in the back of a pickup truck and drove it along a stretch of highway or a road that's about 1 kilometer away from the University of Waterloo's campus, and at night. And so they did a free space link, free space as in, you know, going through the air from the rooftop of one of the buildings on the campus to this truck. and demonstrated QKD to a moving receiver with this concept. And you can see the lens of the receiver here. This is a beacon scope, so a really, really bright light to help with alignments between the transmitter and the receiver. So there's actually a couple different wavelengths of light happening. There's the quantum channel light, and then there's also a very, very strong beacon light that's, again, helping with the tracking and the connection. You can see there's a camera. This is lots of electronics. So every photon in this experiment, we have to have synchronization. So we have special electronics that take the signals from the detectors, and then every photon that arrives, it arrives as like a detection event. And so every event gets its own little time tag. So it's called a time tagger. So imagine little photons are traveling up to a little carousel, and they have to push through to get into the little building, right? So they go tick. Yeah. So we got one of those. And the orange fiber that you see, this orange cabling, that's optical fiber. So that's multi-mode optical fiber that's collecting the photons from the telescope and then sending it down into our detectors. They're fiber coupled. Trying to see where they are, but they're somewhere hidden. And now, because it's a satellite, oh, go on. Do you have a question? Because the receiver has to go on a satellite, there's a finite size, there's a finite weight. You can't use too much power. So, you know, we definitely can't send something this big up in space, right? So over the next several years, the QKD receiver was like basically shrunk down into like very compact detector electronics. And that's what this picture is here. And then a team demonstrated QKD from a plane. So you can see just behind JP's head is the transmitter, or sorry, the receiver telescope. So this plane here is the NRC Twin Otter Airborne Research Craft. So the team went to this location in Smith Falls, Ontario, and demonstrated a QKD free space link from the ground station receiver to the ground station transmitter to the receiver on the side of the plane here. So they actually had to fly, the team had to fly in the plane, all strapped in with door obviously off, so you can actually get the free space link. So that was fun for them. And this is a schematic of our actual receiver. And so all those parts that we were talking about in the BB84 protocol, you can see them here. So these little boxes, they're just wave plates. So it's just a birefringent material that rotates the polarization of the light. This weird looking thing, pentagon thing, is the special beam splitter that they were using. So 50% of the light, it's a non-polarizing beam splitter. Roughly 50% of the light goes to the HV detectors, and then the rest goes off to this DA. There's also a little pick off. That's why there's this little dotted line here. It's just for our own sensors to measure something before it goes off to the detectors. So it's just minor. And then you can see you want to eliminate as many moving parts, as many unnecessary optics as possible. So we literally rotated the DA basis physically from the HV basis so that we didn't have to have additional optics components to rotate the polarization. So that's why you can see here, some of the detectors are straight up and down, and then these ones are off to the side. Okay. And now, so in 2017, the Canadian government announced funding for over 5 years to support new projects as well as the KeySat mission. And so this is supporting Canadian innovations in space. And my prof, Thomas Yanavine, he was named the KeySat Science Team Principal Investigator, and the team was awarded the science support contract. And so hence why I'm talking to you now. And so my role as a science team coordinator, as I said, there's a lot of different people, institutions who are part of this mission. The primary optical quantum ground station, the primary location is going to be in Saint-Hubert at the CSA headquarters. And then the secondary quantum ground station, the quantum optical ground station, yes, we actually had to have our acronyms different, very, very slightly, is at IQC. And so it's going to be on campus. And then we also have a few other partners who are helping with ground stations. For example, the University of Calgary is going to be a tertiary ground station. So we'll be linking out west and hopefully demonstrating a QKD from Calgary to Waterloo and Waterloo to Saint-Hubert and everybody. And these other partners, they might be contributing scientific knowledge, equipment, all sorts of things.
Katanya, fortunately, our students need to run off to their next class, so we need to say thank you at that point. I really appreciated the talk. It was great. Thank you very much.
I was about to pop in and say pretty much the same thing, that we're kind of running out of time.
I know, I gave a little too much preamble, I'm sorry.
No, it's okay, and there were a lot of questions. It's some complicated stuff as we're trying to sort through it, but there were a lot of questions from the audience and from myself because I was trying to sort through it as well. But I see, you know what, I see we're at the last slide as well. So
yeah, I was just coming a little bit to the end there.
No, that's perfect.
Thank you so much for everyone's attention. And if you have any questions, please reach out. You can find me on LinkedIn. You can find our group. This is our QR code for the website. And if you want to learn more about QKD, we even have some YouTube videos out. So this is our little demonstration that we made. And yeah, thank you.
Thank you very much. We really appreciate your time. Actually, could you just stick around for just a moment? Because I have questions I want to ask. But the kids do need to leave because they have to get to other classes, or we have to allow them to get to other classes.
Yeah.
But yeah, thank you so much for your time. We really, really appreciate it.
I have the gift of the gab from my dad. So
Thanks very much, Katanya. I'm going to log off here because other students are starting to come into the room.
Right, yeah, we need the room too, yeah. Okay, thanks, Nick. All right, but I have questions that I wanted to ask, so I'm going to ask them now.
Okay. Cool.
Not so physicsy, more practical. So maybe I completely misunderstood this, but is this whole system reliant on satellites actually moving physically from one location to another?
The trusted node one, yes.
So, yeah. I mean, we're not talking about something that can take place instantaneously or on a quantum level of instantaneousness. I mean, you really have to have this thing physically move through space to get somewhere else.
No, just for that, there's different scenarios. So if you could put an entangled source on the satellite and then have two telescopes, and so the satellite can see like the two ground locations at the same time, then you can have like information transfer and the satellite can be untrusted because you're using entangled light.
Okay.
So it's a different protocol. The one I stepped through today was far easier.
Yeah, it's the easier one.
Yeah, but it's also, that's why it's called trusted node QKD. So we can also have untrusted node where the satellite doesn't know anything. And then you just, the limitation is the satellite has to see the ground station. Yeah, to make the connection. Yeah. So
what's the end goal here? What are you trying to accomplish, like, 15, 20 years down the line with the technology being developed right now?
Yeah, so basically we're working to deploy the quantum internet. So right now we have like the classical internet where we have computers linked with fiber optic cables and all that kind of stuff, right? So if you had quantum computers, you want that quantum information to be also transmitted around the world, you need a quantum internet. So because of what I said before, you can't just send the light through our current infrastructure because it only works over a couple hundred kilometers. And then the fiber is too lossy and the information gets lost into the environment and you can't clone it, you can't amplify it. So you need other ways. So satellites.
What kind of infrastructure would be necessary for that?
That's currently one of my jobs. Figure out what all that is. Yeah,
I mean, geez, I mean, you know, maybe I'm misunderstanding, but like internet's big.
Oh yeah.
I mean, I could see, you know, something for, you know, I don't know, military purposes, but boy, if you're talking about internet, you know, that's how many satellites, how much communication. That seems like it would be incredible what would be required for that.
Yeah, if you think about Starlink, and the fact that Elon Musk is trying to bring the internet to all these remote areas around the world, right? And he's having to deploy thousands and thousands of these small satellites. We would have to deploy a similar level of quantum satellites. Wow. So yeah.
But they're small, right? Yeah. I mean, when you showed that thing in the truck, I thought, oh, that's small. And you're saying, well, this is too big for us to put in space. Too big, yeah. My goodness. Okay, so when you're talking about satellites, you're talking about very small little packages.
Yeah, CubeSat, microsat. So a few hundred, a couple kilograms. Like a CubeSat's quite small. It's like 4 inches by 10 inches or something like that.
Wow. Okay. All right. That's very small.
Yeah. But we need that. Yeah.
Last thing, just out of curiosity, the slide that you showed, the one that had the satellites and then the ground stations, I was looking through them, but I'm also trying to monitor this stuff. So I had stuff all over the place. So maybe I missed something, but did I miss did I miss the United States in there? I didn't see anything from the US in there. And I found that very surprising.
They definitely have a few quantum missions. Let's see.
I would have to imagine so. But
yeah, so the authors of this paper chose not to include.
Oh, okay. Okay, fine. Because there's no way they're not in this in a big way.
Yeah, no, they definitely. So like my prof, he works with the collaborates with the University of Illinois, and they actually just launched CapSat. So the cool annealing payload satellite. It just launched off of the ISS like literally last week. And that's going to be testing if you can do laser annealing of quantum detectors in space. And that'll be the first satellite demonstration of that. So the US definitely has stuff up, but maybe just not like a notable missions like Nicias and stuff. Like China's mission Nicias definitely set the bar. They did a lot of these experiments first. Okay,
well, those were my questions. Thank you so much. I really appreciate it. Boy, that was an interesting talk. Yeah, I know. I'm
cool.
I'm just saying my thank you words. You know, we were talking. I was asking questions. I want this to be in the recording because you know, maybe people who are watching this were thinking about asking the same things. So yeah, thank you. Really, really, really appreciate it. Appreciate your time. I'll be in touch.